So up until now, we've mainly been talking about one random variable at a time, with occasional comparisons. Today we're going to introduce a lot of bivariate topics, things where we simultaneously talk about two random variables. We're going to focus on the case of two discrete random variables today, and we'll look at things like the bivariate probability mass function, and we'll see how do you represent it as a table in tabular form. And then we'll also see the origin of the term marginal distributions to describe things that actually get written in the margins of those tables. And we'll do several examples just to try to get familiar with things. All right, let's go. So what we're really doing here is we're going to extend our work from chapter 4. So extend chapter 4 work on random variables to joint and conditional probabilities. That involve two variables. Two random variables, hence the name bivariate distributions. All right, so that's going to be our primary focus. The first big piece of this is just about discrete distributions. So this is discrete as in the opposite of continuous, so discrete distributions. Oops, can't seem to get that right. We'll just leave it like that. All right, and so the first thing we're going to talk about today is joint probability mass functions, or joint PMFs. And these work a lot like the way regular probability mass functions worked, except we're going to have two random variables. So there's not a whole lot to motivate other than the fact that we have two random variables involved, so we'll just jump right into the definition. Right, so the definition of them. Definition of joint probability mass functions. So we're going to have two random variables. So let's say that you name them x and y. X and y be two discrete random variables. And they have certain they take on certain values. So let's say x takes values that are a discrete set. So x1, x2, and so on. And y takes on values y1, y2, and so on. If you set them up this way, then the joint probability mass function has a really simple form. So the joint PMF, which is the thing we're defining here, of x and y, it's denoted by little f of x and y, like that, where you write it in the following way. So f of x comma y is equal to one of two different things. So if x, I better move this to the side actually. If little x and little y take on one of the values that big X or big Y can take on, then it's the probability that big X is equal to little x, and that y is equal to little y. Right, so that's if x is in this long way to write this, but and y is in y1, y2, like that, right? And then otherwise, if the arguments little x and little y aren't in those sets, then it's 0. I should point out that this isn't written in the notes, but I think it should be. Sometimes it gets confusing which order the variables are meant to be in. So, for example, if you try to evaluate this function f at, say, little x equals 2 and little y equals 3, it'd be like this, right? So it'd be like f of 2 comma 3, but if you just saw that by itself, and you know, like this, and you had forgotten the order that you put in, what is the meaning of the 2? Is that x, or is the 3x? I don't know, I forget. So sometimes to fix that problem, if there's a concern that it might not be clear from context, sometimes people also write this as, they put a subscript underneath it with the big X and the big Y. And we're going to be doing that a lot for other functions that we encounter today. But it's not done for some reason for the joint distribution in the notes. You don't have to do it, and often you will find yourself sort of cursing the fact that you're replicating these symbols all over the place when it's clear what you meant. So you don't have to necessarily do it, but I just want to make it clear that you could write this to try to clarify things for yourself. Okay, so now we'll just write down the main properties. Or rather, the conditions that a joint PMF has to obey. Maybe that's the better word for this, conditions required. Like this is when we checked honesty and positivity and things like that. So one condition is that f always has to be in between 0 and 1. For all the values of x and y. For any value of x and y that you put in there. That's one condition. This is very similar to these conditions are almost identical to the ones for the single variate or univariate probability mass function. All right, and the second one, and this is going to be called honesty. This one just says that if you sum up all the different non-zero values of f, they had better sum up to 1. And so we're going to write that in the following way. So we're going to write, it's sort of a sloppy notation. We're going to write the sum over x, sum over y, and then f of xy is equal to 1. And I think it's a sloppy notation because, you could look at this and say, like, well, what does this even mean? Right here, that's pretty ambiguous. And so what this is the sum. This is really like the sum over x is in the set x1, x2, and so on. But you see it gets pretty messy there. And so we just we will use this notation over here like this all the time because it should be sort of clear from the context that what we really mean is this. So this is sort of a shorthand notation. Or you could just call it sloppy. Because if things get messy, if things get complicated, it becomes confusing. But yeah, so those are the two conditions that we have. Right, now let's try a little example with a joint probability mass function and see if we can make some sense out of it. This example is actually not just a simple example, actually. We're using it as a tool to introduce one of the main things that's used with joint probability mass functions, which is a certain type of table. So it's sort of more than an example. So I don't know what you want to call it, like example plus or something like that. It's a little bit more than just an example, this thing. So let's suppose you have the following joint probability mass function. Right, suppose. So, and I've skipped all the let x and y be discrete random variables and so on. So let's suppose that it's x times y divided by 9 if x is equal to either 1 or 2 and y is equal to either 1 or 2, and then it's 0 otherwise. So both x and y are random variables that can only take on 2 values. We've called them 1 and 2. And then those are the probabilities that it can take. So part 1 of this thing, this so-called example, is to express this as a table. But so this is a way in which it's not really an example, because you might not know exactly what kind of table to make. So you might try, for example, I don't know, I would have probably done this if I had never seen these things before. I'd probably do this, right? Like that. That's not what people do. So we're going to get rid of that. Or at least, I mean, maybe people do that. But that isn't the kind of table that we're trying to introduce. We're trying to introduce a table that looks like a little bit of a matrix. And so it's going to have rows and columns. And in the corner up here, we write f of x, y. This is sort of just like the name of the table. It's telling you what values we're actually tabulating. And then on the horizontal line, we're going to put values 1 and 2. And on the vertical, so both variables in this case take on values 1 and 2. So these guys over here, these are going to be the value of y, and these are going to be the value of x. For some reason it bugs me. I want those to be flipped because I'm used to horizontal axes being x, but nevertheless that's how we're doing it. And so what is the probability? So then the values of f are what you fill in these little spots here, right? And so we'll do that. So if little x is 1 and little y is 1, what is f of x, y, right? So we've got, so we got 1, 1, and then we go up to this equation and evaluate it at x equals y equals 1, and that's a 9th. Right? If little x is 1 and y is 2, then we get 2/9. Right? If little x is 2 and y is 1, we get 2/9. And if both little x and little y are 2, we get 4/9. And this table tells you, so you can make these tables only in situations, of course, where your random variables take on a relatively small number of values. If they take on a huge number of values, you're going to be in trouble. And obviously, this is not going to generalize very well if you want to go to, which we're not going to do, but if you wanted to go to a case where you had 3 random variables or 4 or 5 or something like that, if you're making tables all the time, that's not going to really generalize very well. But yeah, so that's the little table that we're going to create. The second part of the example asks you to do a few calculations. So calculate some probabilities. And we'll just do them one at a time. I think these are actually all written up as different parts of the example, but I'm just going to go ahead and do them. Okay, so the first one is, what's the probability that x is greater than or equal to 1 and that y is equal to 1, right? So we go back up here in this table and we just look, right? So if x is greater than or equal to 1, that's kind of a funny way. That's sort of silly, right? It is only greater than or equal to 1 in these cases. So any value of x, but y is equal to 1, right? So that's what we're after. We're after both of these, right? So we're going to add those up, really. So what we're looking at is the probability that x is equal to 1 and y is equal to 1 plus the probability that x is equal to 2 and y is equal to 2. So really what we're doing is we're summing down the column, right? And so that's 3/9, which is a third, right? Okay, now let's look at the next one. Let's say we calculate the probability that x plus y is equal to 3. Right, so we go back up here in this table, and so when does that happen? So that happens when if y is 1 but x is 2, or if x is 1 but y is 2. Right, so we've got those two different scenarios. So we got the probability that x is 1 and y is 2 plus the probability that x is 2 and y is 1. And we could just add them up. So if x is 1 and y is 2, that's 2/9. Right? If x is 2 and y is 1, that's also 2/9. Let me fix that up a little bit. And so that's 4/9 is the answer. Right? The last one I'm going to do is the probability that x is equal to 1. And if you think about it, this isn't that different. This is quite similar to what we had over here. Isn't this actually? So this is the probability that y is equal to 1, right? Because this thing is a comical way of writing x is equal to any value that it can take on. And so just like this guy, the probability that y is equal to 1 was like a sum down this column. The probability that x is equal to 1, that's going to be a sum along these rows, right? Okay, so this is equal to the probability that x is equal to 1 and y is equal to 1 plus the probability that x is equal to 1 and y is equal to 2. And so we can look up there and add those. 1/9 plus 2/9, so again that's 3/9, which is a third. So it turns out these two guys that we just did, this one and this one, these are sort of special. They're special because we summed along a row or along a column. And I don't know if you've ever used spreadsheets very much, but it's pretty common. I think most of you probably have encountered them, or maybe at least seen them. It's pretty common if you have a table of numbers like this and you're working with them to make like a third column over here where you put in the sum, like that, right? And so you add that way and put the next number there, add that way and put the sum there, add this way and put the sum there, add this way and put the sum there. These areas off to the side of the table, these are sometimes called the margin of the table. And those are that is the origin of the thing that we're about to introduce here. And these are called marginal probability mass functions. Oops, sorry. That's sort of a new topic. I'll go in red. Marginal probability mass functions. And they are really going to be just those kinds of things where you sum along a row or along a column. And the name really does come from the fact that people often do that and then put the result in the margin. So we'll say that on the side. When you sum along a row or a column. And then you often put the result in what we call the margin, or on the edge. Okay, so that's where that name comes from. And so we'll define it here, and then you'll see that it really is just what we were talking about. Okay, so again, we're going to introduce our two variables. So let x and y be discrete random variables with a known joint PDF, or with a joint PDF. Oops. F of x and y. Then the marginal PMF. Oh, sorry. This is a joint probability mass function. The marginal PMF for x is written as this guy. That's if you sum over all the y values, so they're only left with x. So we'll highlight this marginal PMF. This is the one for x. And the marginal PMF for y is written as a little f subscript of y, like that. And then I'll write out what these mean. Okay, so this guy is if you sum over all the possible y values. I'm using that same shorthand notation again. Right? And so that's just equal to the probability that x is equal to little x. Because you've summed over all of the y values, all of the possible y values. And then this one, the marginal PMF for y, is what you get when you sum over all the x values. And that's just the probability that y takes on value little y. Right? You might want to review. So you might want to review so if you want to see why is this true, what we call the total probability theorem. I say that because we haven't used it in a while. I think you only saw it. I don't know how much you used it in the first 5 weeks of the module. Maybe you used it a bunch. But we haven't used it in my portion of the module. So you might want to review it, and that is in, where is it? It's on page 10, chapter 1 of the notes. It's one of the theorems. I think it's a theorem 4.12 in my copy of the notes, but that could change if somebody's like recompiled them or something. Yeah, so that's a theorem. I'll sketch it. So I'll take out this parenthesis and just make a little reminder of what it looks like. It says something like this. So you have to look back there to see what it's talking about here. But it says the probability of some event B is the sum over some index, which you have to look back there to see what it means. The probability of B given A sub I times the probability of A sub I. And that's equal to, I think I need to put that on the next line. The probability of B and A I. Yeah, but so you should look back for review to see how that comes about. I think the requirements here are that the I's here are all of the possible A's, or something like A covers the space of all possible outcomes, or something like that. But again, so go back and review this to see the details of what are the conditions for what is A and what is B here for this to actually work. Okay, now we'll go on to another example. And here we'll use the marginal distributions, and we'll put them kind of where you would put them. So let's say the usual stuff, x and y are discrete random variables, and they have a joint PMF. F of x comma y, and it's in table form. This has got some sort of long numbers in there, so I hope you'll just bear with me here. So I'm going to write it like this. Might need a little bit of space here. Yeah. Okay, so this is f of x, y. So I'm just making a tabular probability mass function. Let's say x can have only 3 values, 1, 2, or 3. So these are the x values. And let's say y can have 4 values, 1, 2, 3, and 4. So those are the possible values of y. I'm going to need to erase a bit more. There we go. Okay, and they have some sort of funny looking values, I'm sorry to tell you. So 0.04, I'm just copying what you'll see in the notes, the exact table. 0.02, hopefully without making a mistake. 0.08. Probably we should have a simpler example. 0.17, 0.05, 0.08, 0.20, and then 0.09, 0.03, 0.06, like that. Okay. Now, the question is to find the marginal distribution. So find and the marginal distribution for y. And again, to do that, what you really do is you just sum down the rows and the columns. And so let's make a little table as if we had done that. So let's say x, and then we have probability that x is equal to x. So just give me a little table. X can have values of 1, 2, or 3. And again, this is equal to, like that. So that's what the notation means. So okay, fine, that's a lot of writing. What is the probability that x is equal to 1, right? So here's all, this row is all of the probabilities where x is equal to 1 for all the different y values. If you add those up, let's see, what do you get? That guy and that guy give 0.1. That guy and that guy give 0.1. So together, those give 0.2. And then you do the same thing for the second row. I'll just tell you the number. It's a half. And you do the same thing for the third row, and you get a 0.3. All right? And if you did this, so what you normally would do, So let's do the following. Let's put this in a certain. Sorry, I'm going to make these. Make these red. And on the side over here, I'm going to put in red those values. So 0.2, 0.5, and 0.3. So it's common to kind of do this. And so I'll kind of put I'm really kind of crowding up this table like that. I better make that more clear. Like that. And then let's say we use a different color for the y's. So I'm going to make y, make a little table. And this is the probability that big Y is equal to that little y. And again, that's equal to the marginal distribution of y. And so this one takes 4 values, 1, 2, 3, and 4. And I'll save you the trouble. I'll just write down the sums. So this is 0.3. So again, 0.3 is what you get if you add up all of these, right? And if you add up all of this column, you get an entry for here. You add up all of this column, you get an entry for here, and so on. And so I'll just write them down. So this next one is 0.1, 0.2, and 0.4. And so what we would normally do, well, I don't know about normally, but it's common to do this. You then put f of y, and you put in these numbers, 0.3, 0.1, 0.2, and 0.4. And so you've put these things in the margins, right? So that this is a margin. And so is the columns, so is the red stuff over there on the side. Notice also, if you just kind of like, if it should make sense to you, I hope, that if you add up all these things, right, what should you get if you add down this column? That's adding up the probability that x is equal to such and so, and you're looking at all the possible such and so's, right? So that should give you 1, and it does. And in the same sense, adding all along there should give you 1 as well. So you could, if you wanted to, you could put a 1 there to remind yourself that that's what the grand total of all these probabilities is. Yeah. So that's just a little demonstration of how to kind of tabulate these joint probability mass functions and tabulate the marginal distributions, and really to kind of give you an idea of the name marginal distribution. Where does it actually come from? All right. So now we'll get to our last new topic for today, the conditional probability mass functions. And these guys, again, we're just going to dive right into the definition and then kind of talk about it. So the definition looks like this. So you'll again start with 2 random variables, because this is bivariate, x and y, be discrete random variables. And then we're going to introduce 2 different conditional probability mass functions. So I'll say the conditional probability mass function for x given y is the following: f of x given y, little x given little y. So you see how this notation starts to get kind of almost like annoyingly repetitive. But there are lots of scenarios, not so much in the definitions, but in use, where it's important to keep track of that subscript. Although it is actually going to come up in the definition here too. So here's how you define it. This should look familiar to you from chapter 1. Oops. Like that, right? And then we're going to similarly, so I'll highlight this. This is the conditional PMF for x given y. And then I'm going to copy this. Maybe I won't. I'm just going to write it again. The conditional probability mass function for y given x is the same thing, but with the letters swapped. Right, and then the formula looks again the same, but with the letters swapped. So there's no point in swapping the numerator. It doesn't matter. The order is not important here. Like that. Okay, so that's our definition, and I guess we'll highlight that too. Right, so this is really kind of a definition for, it's like sort of two different examples, and so you should see why the subscript notation kind of needs to be there. Maybe you don't see it so much because the arguments here, little x and little y, none of them are numbers, they're symbolic things. But if they've been like numbers like 2 and 3 and 4 and so on, it really gets confusing. You can't tell. It's rare that there's a context where you can actually tell what's what. So we're going to do an example, and this example, that problem won't come up because we're going to put little x and little y to be the same values for the most part. But you can certainly imagine scenarios, most other scenarios, it would make trouble. So this is a little example. It's kind of a fun example that we're going to use to kind of close the show today. So we want to think about a machine that has sort of two different subsystems. In the notes, it's like a nuclear reactor or something. I feel like that's a little bit dramatic. But so let's take just some machine, so like a car, or I don't know, or house. Consider some machine with two subsystems. What is a subsystem? I don't know. Like it could be a cow. The machine could be a cow, and one subsystem is like the lymphatic system, and one subsystem is the nervous system, something like that. It doesn't have to be a nuclear reactor, which is what it is in the nuclear power plant in the notes. So we'll call those A and B. Right? Now we're going to make two random variables that go along with those things. So let's say let x and y be discrete random variables. And they have the following, describing them. So we'll say x is equal to, it has only two values, right? It's going to be 0 or 1. It's 0 if subsystem A fails. And maybe there's a different value of x for every day. So we'll say on a given day. And then it's 1 otherwise. So assuming you want these subsystems to not fail, 1 is the good number to have. And then I'm going to copy this because y is going to be made similarly, but it's for the other subsystem. I can probably move this down a bit to space it out. Okay, and so y is going to be here, and it's for the other subsystem. right? So these are just some sort of measure of whether or not the systems are working. And okay, so we'll write down their joint probability mass function. So they have the following. Oops. Joint PMF. F of xy, which takes a table form. And we're going to make this thing so that the subsystems, for the most part, are kind of working. So it's going to be 0 and 1, 0 and 1. Again, this is for x, which is referring to subsystem A, right? And these are the values of y. I think I need to move this 1 over a bit. So this is talking about subsystem B. I need this sort of long horizontal space because of the numbers here. So the probability for both of the subsystems to fail, A and B, so that's y is 0 and x is 0. That's 1 over 20,000. The probability for x equals 0 and y equals 1, that's 1 over 10,000. All right, and the probability for y equals 0 and x equals 1, that's 1 over 10,000 as well. And the probability for both to be 1, which means everything's fine, right? Both systems are working. That's close to 1. 19,995 over 20,000. Oops, not 22,000. So 5 out of every 20,000 days both fail, say. Right? So that's what this says. Now, what do we want to answer here? Well, we're going to answer some stuff, but before we do it, since we made this table, right, we may as well make the marginal parts, right? So I'm going to put them both in black. And just add them up. Right, so this is if you sum across the rows, sum across this way, you've summed over all y values, so you're left with this guy. Right, and what do you get if you sum the first row? You get 1 over 20,000 plus 1 over 10,000, so that's 3 over 20,000. And the bottom one, 1 over 10,000, that's 2 over 20,000 plus this other number, so you get right. Of course, if you add those down, you get 1. And so for the in the same way, we have here f, the marginal distribution for y. I'm putting these marginal distributions in here because they're going to be useful for computing conditional probabilities, which is what we're going to do. Okay, I think we get the same numbers here. Yeah. So this one is 3 over 20,000. And this one is, again, 19,997 over 20,000. Yeah. Okay, so that's tabulating everything. Now let's get to the actual question at hand. All right, so I haven't even asked the question here. So we just have these. I just couldn't control myself with this table. I had to fill it out. So these are these two random variables. X tells you if subsystem A is failing or not, or fails or not, and Y tells you if subsystem B fails or not. And what we want to do is we want to find out. So we want to find the probability that X is equal to 0 given that y is equal to 0. Now you can't just look up here and see this. It's not the probability that x and y is equal to 0, right? It's the probability that x is equal to 0 given that y is already equal to 0. So one of the systems fails when the other one already has. So what's the chance of that happening? And so that is, you can write that out using your definition of conditional probabilities or Bayes' theorem, or however you want to say it. It looks like this. So it's the probability that x is equal to 0 and y is equal to 0 divided by the probability that y is equal to 0. Right? But all this stuff, you can translate it into our probability mass functions. And so what this is oops. So what this is f sub x given y 0, 0 is equal to f 0, 0 divided by f sub y 0. And now we can actually evaluate it because we can look up here, right? So the probability that f0, 0 is this value here, right? And fy at 0, that's this value here, right? And so this is equal to, what do we have here? 1 over 20,000 divided by 3 over 20,000, right? Which is a third. So that's interesting. That's much bigger than this number by itself, right? So, okay, so that's a third. So the probability of system A failing, given that system B has already failed, is a third. It's not the same thing as asking the probability that system A and B fail. That's a quite low probability. But if system B has already failed, then there's a high probability that system A is going to fail. This sort of fits with like the biological context. If one of the systems of the body fails, then the other ones are under stress and might also fail. Okay, and so it turns you can do this same thing that the exercise in the notes has you do the exact same thing but with x and y in reverse. So it says also find the probability that y is equal to 0 given that x is equal to 0. And this is sort of anticlimactic because so what it is, you can write it like this. Right? Everything is the same except the x's and y's are swapped. But the reason that's kind of a bit of a bummer, I think, is that this table is symmetric about the diagonal, so nothing changes. And your answer is again a third. So okay, fine. It just means that for both of these, so if one of these systems fails, there's a high chance that the other one will fail. That's what this is saying. It doesn't matter which order you put the systems in, right? And so that's kind of emphasized. So we'll just remark. So notice this is kind of important. This probability that x is 0 given y is 0 is big compared to the probability that x is 0. Right, the probability that x is 0, if you go back up here and look at the marginal thing, right, that's just here, 3 over 20,000. So this guy is 3 over 20,000. But the probability that x is 0 given y is 0, okay, that's not in the table, but we just worked it out. That's a third. So it's much, much bigger, right? And the same is true when you switch them. So I'll put those in there as well. Because of the symmetry here. So if this were some really important thing, like a nuclear reactor or a biological system for like a crucial animal or being or something, you can see that this is really important. So I'll just emphasize one last time the probability that x is equal to 0 and y is equal to 0. So that's in the table. We've talked about that, so you go back and see it. Right? That's this number here. The probability of both failing, that's low. It's 1 over 20,000. But it's not at all equal to the probability that x is 0 given y is 0. So if one of the systems fails, that's a third. Also known as about, let's see, do I have that right? I do have that right, but this is not quite how I wanted to emphasize this. So let me get rid of this line here and point this out. So I want you to see what this is not equal to. If you naively thought about, okay, there's a low chance that system A fails and there's a low chance that system B fails, you might think that gives you the 1 over 20,000, but it does not. So this is not equal to the probability that x is equal to 0 times the probability that y is equal to 0. Right, if you did that multiplication, that would be 9 over 40,000, right, which is about equal to 22,222 times this one. Right? So what does that mean? You should be able to say, if you think about it. I don't know if you... So what does it mean when the joint probability is not equal to the product of the individual probabilities? Right? So I'm going to put it down here, and then we'll be done. So x and y are not independent. And we will get back to this later on in the chapter. We'll talk more about this independence. All right, I hope you enjoyed that just initial introductory coverage of bivariate topics. We're going to spend a lot more time on bivariate topics as we go forward. And in the next lecture, we'll see what happens to expectation values, and we'll start to dig into continuous cases. I'll see you then.